Now the function here is fx is equals to x or x square. So when it is x and when it is x square, I mean x if x is greater than equal to 0, and x square if x is less than 0. So that means it is defined on all the points. On all, for all real numbers it is defined. So now we have to discuss its continuity. So in order to do that, we can actually even draw the graph first if you want, or we can start with solving this. So anything we can do first. Let's draw the graph of this function first. Right. Now here again it has two parts, that is x greater than or equal to 0 and x less than 0. So when x is greater than or equal to 0, it is, you can see y is equals to x. So that is actually a straight line. So by now you must be aware of such graphs and such simple function, that it will be a straight line. So this is our graph, y is equals to x, right? So if x is 1, y is 1. So this is 1 comma 1, this is 2 comma 2, this point is 3 comma 3. So this is our graph, y is equals to x, or fx equals to x. Okay, coming to the next part, that is x square. So this second half is, or the portion of the graph which is to the left side of y-axis, or left side of x equals to 0, that is actually function square. So 0 square is 0, so it will remain here. But before that, if we go say minus 1 square, so minus 1 square is 1, right? So this is a point. Then minus 2 square is actually 4, so this is the point. Then minus 3 and so on, right? So we know that this is a parabola. So the graph will be like this. Next point at 3 it will touch 9, so it will go like this, right? So this is the graph. You can see this is a parabola, and after parabola it becomes a straight line after x equals to 0. Now from the graph itself, we can see that the function is defined at every real number, and graph of the function, by inspection we say that we can again partition the domain into two, or yeah, into few sets. That is, this domain can be partitioned into say 3, that is d1. d1 is your real numbers less than 0. So this is actually, or if you have to write it properly, you will write x that belongs to real number such that x is less than 0. Same way d3 is x, a set x, that is domain. We are defining the domain of all real numbers such that x is greater than 0, and d2 is just 0. So these are the three different domains, and we have to discuss, or we have to find its continuity in all these domains, the three domains or subdomains. So here, let's do it case by case. That is case 1, that at any point in the first domain, right? So in that case, what is the function? Function is here. You can see that is fx is equals to x square, and we know that it is a continuous function. If you have to prove it, you can again do it the same thing, that is, let x tends to some point c, c belongs to d1. So limit of this function f of x So that is equals to limit x tends to c x square, and that is equals to c square. So that is the limit. Then we find the value of that function at x is equals to c. So that will be equals to c square. So these two, because these two are exactly same, so we say that limit is equals to. So what does it mean? That this limit is equals to value at all points in the domain. So this is continuous. So that's why it is continuous in D1. And similarly, you will be able to prove it in D3 as well. Say in D3, case 3, that is at any point in D3. So our fx will be actually equals to x. So again, limit x tends to c, f of x is equals to limit x tends to c, x is equals to c, and f of c will also be equals to c. So continuous, right? And what is the third part? The D2, which we have seen, that is at x equals to 0. Now at x equals to 0, you have only the value. How are you going to find the value? So that is again little, I mean, from the figure you can already see that the limit is also 0 and the value is also 0. But we have to do it in systematic way. So at x is equals to 0. So we have to first find the limit. So limit at any point if you have to find, and if there are two different functions at that is when at 0, if you approach from this side, the function is x square. If you approach from this side, the function is fx equals to x. So we'll have to find limit from both the directions. So we will have to actually find left hand limit, that is limit x tends to 0 from negative side f of x, and this is equals to limit x tends to 0 negative, and f of x is x square. Now that is equals to 0 square or is equals to 0. Same way you find the right hand limit, and right hand limit will be what? Right hand limit will be limit x tends to 0 from the positive side f of x. Now this f of x is actually, what is f of x in the right hand side? It is x. So limit of x, and that will be equals to 0. So now both the limits are equal. Both the limits are equal, and that's why we'll say that because LHL is equals to RHL, that's why limit when x tends to 0, f of x is equals to 0. Done. So limit is 0, and that limit is actually equals to f of 0, which is equals to 0. So that's why this is continuous at every point, or this function is universally continuous. Right? So that's how such complex problems or complex functions, which are not actually complex at the moment, you can see that these are just easy functions. Only thing is we should be able to draw their graph, and we should be able to write it in a systematic way, the way people expect us to write. We should write it in that way. Otherwise there is nothing here so difficult, and it's actually very easy concept. Now let's move to the next question and see a little more complex function. Not that we won't be able to solve it, but you might have not seen it, or if you have seen it, you must have ignored it something like that. So we have to find the point of discontinuity of the greatest integer function. So the function is greatest integer function. So first thing is we should know what is this function. So this was there in your 11th standard. If you remember it, it's good. If not, I'll just revise it for you. Greatest integer function is actually shown or represented as fx is equals to a square box, and in that there will be x. So x denotes the greatest integer. But what greatest integer? What is x doing here? So this means, or to understand it simply, I'll write greatest integer about this. This is the greatest integer less than or equal to x. So whether we understood it or not, let's check that. What will be the greatest integer function? That is, what will be its value if instead of x I am writing 3.5? Anyone knows, can answer fast. Greatest integer function of 3.5. Yes. Reply. Whether you understood it or not. Am I audible or not? Yeah, Vaibhav. So tell me the answer. Roshna, you are not. I'm not audible to you. Okay, no problem. Whoever is able to hear me can answer what will be the greatest. What will be the result of this greatest integer 3.5? The definition in the purple is the real definition. That is greatest integer less than or equal to x.
Three.
Was someone saying something?
Sir, is it 3?
Yeah, it is 3. Okay. And greatest integer function of minus 3.5?
-3.
Okay. Let's check this. Let's draw the number line first. Right? Suppose this is R0, 1, 2, 3, 4. This side -1, -2, -3, -4. Right? So when I said 3.5, 3.5 is actually here, right? This is 3.5. And when I said -3.5, where will be -3.5? It will be here between -3 and -4. So this is our -3.5. Now tell me the greatest integer function of -3.5.
-4.
It is -4, right? So it's not -3, it is -4. And I hope all of you understood the concept of greatest integer function. So that's what greatest integer function is. That is, you have to find out the function which is you have to find out the number which is less than, or not any number, the integer which is less than or equal to greatest integer but less than or equal to x. Right. So if it is just -3, it will be -3. If it is 3, it will be 3. But if it is -3.5 and 3.5, there is the difference. So you have to keep that in mind. So now we have to discuss the continuity of this greatest integer function. So we should be able to draw the graph of that function first. So let's try to draw the graph of that function. From that graph itself, it will be clear. I'm drawing the graph of this function, that is the greatest integer function. So now from say 0 to 1, if I move from 0 to 1 till 1, I'll have only one value, that is 0. I mean, at 1, if it is 1, greatest integer function of 1 will be 1, but greatest integer function of 0.9 will be 0. Greatest integer function of 0 will be 0. So from 0 to less than 1, it will be all equal to 0. And then, as we have seen, at 1 it will be equals to 1. At 1.5 it will be equals to 1. At 1.9 it will be equals to 1. But as soon as you reach 2, it will become 2. So from 1 to next, from integer to integer, it is actually all constant values. That is, either all will be 0, or all will be 1, or all will be 2, like this. So if I have to draw the graph of this function, I know that from at 0 it will be 0, and then from 0 to 1 it will be like this, right? And at 1 suddenly it will go and become 1. And from 1 to 2 again it will be like this. And again at this point, these are the points, right? Like this. Here it's not like this. And again at 2, I mean, this is what, this is 1, this is 2. So at 2 it won't be 1, it will be actually, so you can see that I have to, this graph is completely discontinuous. I mean, in this much time itself I have to do this. I have to lift my pen so many times. I have to lift my pen up. So next point will be, next portion will be straight line till here. Again at 3 it won't be 2. At 3 it won't be 2, it will be actually 3. So this is 3. So this is how the graph looks like. And that's why this function is also called step function. Right? And before that, that is say from -1 to 0, it will be actually -1, right? So again, this is the point of discontinuity, and from here to here it will be like this, right? So let's draw it like this now. Right. So this is how the greatest integer function looks like. And from the figure itself, we can observe that it is defined for all real numbers, no problem in that. But there are lots of points of discontinuity. And what all are the points of discontinuity? These, where I have to lift the pen. Where I am lifting the pen? At all integers. So this function is continuous or continuous except the points which are the integers. So we say that this is continuous, or let's say this is discontinuous at all integers. Right? So all integer values it is, so that means all those x which belong to integers, it is discontinuous. Now the same thing, if we have to do it mathematically, that is by finding the limits and all, so I leave that to you. So I have left actually one more question to you, that is this part to you to solve. So, and today this is the question which I am leaving for you to solve, that is graphically I have shown you what do we mean by greatest integer function and how to find its point of discontinuities. Next is you try to solve it the way we have solved it here, like finding limits and then saying whether the limit is equal to the value or not, or whether the limit exists or not. So try to do that, see if you are able to do it. If not, I'll try to solve it in the next class. So that's all for the time being for today, and we'll have our next class tomorrow. And what else? That's all.